here. So this is a joint work with my supervisor Dušan Knop and with one of their PhD students, my colleague Šimon Šírek. So as the name suggests, we will be spreading some virus. So let's start with brief motivation. So our setting is that let's suppose we have this graph with nodes A, B, C, D, E, F, and G, and moreover, suppose that so in our model, all the vertices have some immunity values. What exactly that means is that, for example, if node C has an immunity value of 3, it means that whenever 3 of his neighbors get infected, then he gets infected as well. For example, if my threshold is 1, I will just confuse the names thresholds and immunity and so on. So for example, if we so now the task is to start a spread, right? So for example, if I started the spread from the node E, let's go back. So for example, if I started the spread from node E, now the process stabilizes here because now there's no additional vertices that would get activated, right? So maybe I could start the process from nodes E and B, but still there are no other vertices that would get activated because there are no black vertices which will have the number of red neighbors, at least the number of their threshold. But on the other hand, if I started the process from vertices E and A, now in the next round, the vertex D gets infected because he has one infected neighbor, which was the A. Now the vertex C is activated because he has 3 active neighbors and his threshold was 3. In the third round, the vertices G and B become infected because their threshold is 2. And lastly, in the fourth round, the vertex F is infected because he has threshold 2 and he has 2 active neighbors. So the task here is to start the infection process in some vertices such that so that there may be many many different scenarios, but in our scenario, the goal is to have everyone in the graph infected. So okay, so I was talking about spreading a virus, but one can imagine that it doesn't have to be necessarily a virus. It can be, for example, a spread of opinion. So we would like to maybe bribe some agents in our network such that they spread the opinion in the whole network. So this could be it, and of course we can model some spread of disease in a network. So okay, let's start with the formal definition. So the definition or this model originally comes from Campbell, Kleinberg, and Tardoš. So the model is as follows. So we have a simple graph with vertices V and edges E, and there is this threshold function which we call T, and we have some initial set S. And now we start the process as follows. So we set S0 to be the set S, and and then we iterate in the I+1 generation. We add all the vertices from the previous iteration, and we include all vertices such that the intersection, like the size of the their neighborhood that is already activated, is at least the threshold value. And of course, we say that the initial set was a target set. If it happens that in some iteration I star, Si star is equal to the whole set of vertices. And as you can imagine, there is a natural decision problem associated with this, where we have as an input the graph, the threshold function, and some parameter k. And the question is whether there is a target set of size at most k. Okay, so and there is a simple observation. So one particular scenario is where the threshold is set to be the degree. So for example, my threshold value is equal to the degree. And yeah, so by the way, if I mention something that is not clear, just feel free to ask me during the talk. So the first observation is that when I set the thresholds to be equal to the degree of a vertex, then this is equivalent to the vertex cover. So just to recall, in a vertex cover, the goal is to select a set of vertices such that every edge has at least one end in the set. So to prove this, so suppose that we have a vertex cover, then it's not hard to see that in the first round, everyone else gets activated, because if S is a vertex cover, that in other words means that either for each vertex, it is in the set, or all of his neighbors are in the set, which precisely means that either he's activated in S0, or all of his neighbors are active in S0. On the other hand, if we do not have a vertex cover, that means we have some HE with endpoints U and V such that the intersection with E is empty, but that means that the vertex U has to be active before V, and vice versa, which is quite impossible, right? And what follows is that the problem is indeed NP-hard, right? Okay, so since it generalizes the NP-hard vertex cover problem, the natural question is whether there are some like natural restrictions of the threshold function that would save us. So there are these scenarios of the threshold functions that are commonly studied. So one of these the anonymous thresholds, which is basically the vertex cover problem. And there is the majority thresholds, which is a generalization where the threshold is like half of the degree. So that would be like reasonable in the influence spread, because like I will adopt the opinion if at least if the majority of my neighbors would adopt it. And then there is a constant threshold where the thresholds are like bounded for some constant. And so for some known results, so let's start with some trivial case. So for example, if thresholds are at most 1, then this problem is indeed trivial, because it's not hard to see that like if I get a connected component in the graph and then I activate the vertex, then everyone else gets activated in the component. So this yeah, of course, if the thresholds are at most 2, then the problem becomes NP-hard indeed, even when the maximum degree of the graph is constant. This can be strengthened to thresholds at most 2 and the maximum degree to be at most 3, which is kind of the very tight bound, because in graphs of degree at most 2, this becomes again trivial. On the other hand, if the thresholds are exactly 2 and the degree is at most 4, then it's still NP-hard. On the other hand, you can solve it in polynomial time when the degree is at most 3. So there's like this very tight bound for solvability and NP-hardness. Of course, the majority thresholds are also hard, as you could guess. And as in classical results, so it's linear time solvable on trees and graphs with diameter 1. In other words, graphs with diameter 1 are cliques. This was also in this work of Nichterlein et al. They considered the yes.
I wanted to ask, what is the intuition behind the fact that allowing CV to be equal to 1 makes the problem harder?
I mean, it's not harder when TV is equal to 1. It's only harder and trivial, because
no, it's harder in your first bullet, because if you disallow 1, you can go for G.
It's yeah, but that's a good question. So the intuition behind why it's hard if we disallow 1 is because like imagine you have a vertex with 1, and then you can like spread the opinion from the vertex into many neighbors. You can like have a 1 vertex and active, and then you can like spread it to a binary tree, and that's what makes it like hard. But like turns out to be in the I don't know if I answered the question, but yeah. So
that was less processes, less local, something like this.
Yeah, like I mean, it only depends on the 1 vertex, and it's like I don't know if I can maybe have a deeper look into that after. Okay, so anyway, so for the diameter, there was this idea that because this was of course inspired by some real-world social networks, that these graphs have small diameter. So maybe what if the diameter of the network is small? So yeah, if the diameter is 1, then the problem is solvable. But as you could have guessed, it becomes NP-hard on diameter 2. So no tractability here. And of course, there are some strong inapproximability results. So in particular, it cannot be approximated within a polylogarithmic factor unless some weird theoretical complexity thing happens. And for the last tractability result, I will mention solvability in interval graphs with bounded thresholds, which will be somewhat related to what we do. So let's get back to this picture. And our main motivation was the spread of a virus, and especially in the recent, or not very recent, pandemic of coronavirus. The idea was that the individuals would have some social distancing requirements, and this picture already suggests that we could model every individual as a point with some personal space, which could be, for simplicity, a closed disk, right? So this brings us to the class of disk graphs. So a simple graph with vertices v1 up to vn is a disk graph if there is some representation of the vertices with closed disks, so the disks are d1 up to dn, such that there is an edge between vi and vj if and only if the corresponding disks have non-empty intersection. And so moreover, if all the disks have the same diameter, then we call it a unit disk graph. There is some interesting family as well, which is the disk contact graphs, which means that we only allow the disks to touch, not like have big overlaps. So they can only touch in one point, or at most one point. And there is a known folklore theorem about these contact graphs that these are precisely the planar graphs. Yes, this is precisely what one would call an intersection graph, where the family is taken to be a set of closed disks in a Euclidean space, two-dimensional Euclidean space. Okay, so for example, this graph from the first motivation is a unit disk graph because here is the corresponding disk representation. So for example, the red vertex has the blue and the yellow as a neighbor because their disks intersect, so on. So these are our results for this problem. So our attempt was to explore whether restricting the graph to unit disk graph would help. Unfortunately, we have all these hardness results for all possible scenarios. Well, in fact, we restrict ourselves to even a simple case, which is the class of grid graphs. So a grid is just it's just a rectangular grid of vertices, to explain it, just take an integer grid and connect all neighboring points. And a grid graph is a subgraph of grid. In two dimensions. So in fact, okay, I will have it on the next slide. Then the disk contact graphs is the class of planar graphs, and there is this there's the class of interval graphs, which is also an intersection graph family where you don't take disks, but you take closed intervals. So yeah, and the results hold even if the degree is very small. So here's another picture to see the relationship between the classes. So the disk graphs are on the top. There's a superfamily of every considered class. Then there are the subfamilies of disk contact graphs and unit disk graphs. And the subfamily of these two is the class of grid graphs. So you can imagine that the grid graph is also a unit disk graph because you can place unit disk on every grid point, and these intersections will precisely be there. And on the other hand, there is this class of interval graphs. So it's not hard to see that whenever you have intervals, then you can draw a circle around every interval to have a disk graph. And uint is the same as udisk, but you have all the intervals have unit length. So okay, so for the proof, so I didn't mention that these squares correspond respectively to anonymous, constant, majority, and general thresholds. Okay, so for the proofs, so let's start with the simple proofs. So the anonymous thresholds. So just to recall, anonymous threshold setting is basically the vertex cover. So here it's like not that interesting because it's just the vertex cover, which is pretty well known on these classes. So let's just recap what is known. So vertex cover is known to be hard even in unit-disk graphs and in planar graphs. So it immediately follows that we get the hardness on unit-disk graphs and planar graphs. However, on grids, it's not hard to solve vertex cover because they are bipartite. There's a standard algorithm for matching, which can be turned into vertex cover because the graphs are bipartite. And in interval graphs, as you could have guessed, it's also solvable even in linear time. Okay, so this was a warm-up. So let's go to the case of constant thresholds. So maybe you noticed that because the hardness of vertex cover is not only in planar graphs, but in free regular planar graphs, which follow it immediately follows that because we are setting the threshold to be equal to the degree, but the degree is free. So we already have the hardness for planar graphs, right? So now it's time to do it for the disks. What we do is like we pretty much follow the same scenario, but we first need to show an auxiliary lemma that independent set is NP-hard in free regular unit disks. So how do we solve that? So we start with the independent set on free regular graphs. And yeah, so because the graph is free regular, it has a degree at most 4, which means you can, there's a theorem that you can always draw the planar graph like this, that you embed the points into the grid, and you draw the lines you draw the edges as straight line segments. So here's a attempt of 3 regular graphs. So what we do next, we would make these vertices unit disks, and then we would subdivide each edge sufficiently many times, and it has to be, for some technical reasons, it has to be a multiple of 6. And trust me, it's doable in some, but it's rather technical to explain the details. But okay, so now we have subdivided the edges, but I promised to have the graph free regular, so that's what we why we have a multiple of 3. So we could like replace so we duplicate every third vertex starting from the second. So now the graph is indeed free regular. Now it is like not hard to see that when I have a independent set in the original graph, then I can just insert the remaining vertices on the path. So like setting the budget appropriately, because we have a even number of disks, then this reduction works. So so because independent set is hard, it follows that the same result holds for vertex cover, because there is a equivalence between vertex cover and independent set when it comes to NP hardness. So it's the same reduction, just reduced from vertex cover. And, so target set selection is NP hard when thresholds are at most 3. Okay, but I promised that, or at least in the known results, there were thresholds at most 2, right? So so how to do it for thresholds at most 2? So we cannot longer use vertex cover because vertex cover is not hard on two regular graphs, right? So there's the reduction from the set, and we use this very restricted version called restricted planar set, in which the restriction is that every variable occurs exactly 3 times, and it is of course 3 sat, so every clause has size at most 3. And the occurrence of the variable is that it's twice as non-negated and once as negated. So we create 2 types of gadgets. We have a clause gadgets, which are simple vertices with threshold 1, and variable gadgets, which are here's some technical construction, but here's the general idea. So here's the example of a formula. These are just simple vertices with threshold 1, and then there is technical construction for the variable gadget, but the main idea is that the target set selects the assignment for the variable. So for example, here, only satisfying assignment is x1 set to true, x2 set to false, x3 set to true. Now in some constant number of rounds, because the assignment was satisfying, it activates all the clauses. So for example, the x1 has the true part, like these two edges correspond to the true part, so they activate the corresponding clause. And now because all clauses get activated and all the vertices have the remaining occurrences, then in the next round, like everything else is activated as well. And by the construction, we can also prove the other direction, where in the opposite way, when we have a target set, we can assume that there is exactly one vertex selected in each of these variables. So we reconstruct the assignment for the formula. So this reduction already implies hardness in planar graphs when the degree is at most 4 and the thresholds are at most 2. But to make it a grid, so again, obtain this nice embedding, and now all we have to do is just subdivide it sufficiently many times. So to be a bit pedantic, so I wanted a grid graph, and we take a grid graph to be an induced subgraph, but this is indeed not an induced subgraph because, for example, this edge is missing, right? So we fix that by dividing even more. So, and it remains to say that the new vertices will have threshold 1, and it's not hard to see that, like, if I insert a vertex with threshold 1 on an edge, then nothing changes with the activation. Okay, so this would conclude the constant thresholds. So for the majority, so in fact, we can take the reduction from any target set selection instance, and the idea is just to observe that if the threshold is too large, then it's enough to add sufficiently many leaves to the vertex, and the leaves will have threshold 1 and degree 1, which is indeed degree over 2, or at least the ceiling. And if the threshold is small, then there are these cherry gadgets which basically ensure that they have to be activated by some. Okay, so let me show you the example. So for example, if I have a threshold 1 and degree 4 in the original graph, then I will add these two gadgets, and the idea is that in every cherry, a vertex has to be activated from, like, in the initial target set, and this ensures that basically the activation process doesn't change in the original graph. And with a slight change, that now we have a majority threshold, so this setting is still hard. And you can imagine that, of course, I can do it in a way such that the graph remains planar. So the proof is the same, and I would have to go into the technical construction, but in the gadgets there are not many vertices which have their threshold not equal to majority. So this still holds even with majority thresholds. So this problem is NP-hard in planar graphs, and observe that we can employ the same idea, just subdivide it once, twice, and because subdivision creates vertex of degree 2, threshold 1 is exactly 2 over 2. So this is easy. Okay, so let me conclude. So these black boxes correspond to our results, and the two green boxes that are not black in int and uint correspond to the result of Bessie, and the yellow ones are unknown. So, of course, a natural question is that whether we can extend, or is there any tractability results for general thresholds in interval graphs, or maybe it's hard in interval graphs but tractable in unit interval graphs. We don't know. And then there is this question whether we can reduce the degree to be free, because for now we have degree 4. And also, so there's another direction to follow. We, in fact, not only have thresholds at most C, but we have thresholds exactly C. So I showed you how to do C equal to 3. The very same idea holds for C equal to 4, but you start the reduction with 4 regular graphs, not 3. 5 regular graphs. There is this technical issue that we no longer have the very nice planar embedding, so we don't know how to do it there. And okay, so I didn't show you C equal to 2, but it can be done in some clever way on the grid. I'm not going to go into this. I can show you if you ask me after. And of course, C equal to 1 is trivial, but we don't know anything about C equal to 5. And as the problem is hard to even approximate, so a natural question is whether maybe the class of unit disk graphs allows for some efficient approximation with some provably good ratio. Yes, and that's pretty much all I have. So thank you for your attention, and now it's time for questions.